Hi friends, today I am giving a lecture on master theorem in design and analysis of algorithms. Master theorem is a particular theorem. That theorem is used for finding the time complexity of a particular recurrence relation. Okay, so it is a shorthand way to find out the time complexity of recurrence relation. Okay, so in the previous videos of master theorem, we are already solved six example problems. So how to find out the time complexity for the given recurrence relation using master theorem. Okay, that we are discussed in the previous videos. Now in this video, suppose we are giving a particular code. For that code, how to write the recurrence relation. Once we have write the recurrence relation, then how to find out the time complexity of a particular recurrence relation. Suppose if the given recurrence relation is not there in the standard form, okay, how to solve that recurrence relation? This is completely different from previous videos that I am done on master theorem. Okay, now this is the given code. So form a recurrence relation for the following code and solve it using master theorem. So this is the given code. For that given code, first we have to write the recurrence relation. Okay, now we have to check our recurrence relation is in the standard form of master theorem. If it is not there, first we have to convert into standard form. After that, we have apply the master theorem. This is the procedure we have to follow in this video. Okay, so here this is the given code. S of n, brace begin, if n less than or equal to 1, if the condition is true, return 1. If the condition is false, else return s of root n brace close. So this is the given code. Okay. So first we have to write the recurrence relation for that code. Okay. So here there are two conditions are there. Okay. First condition, if n less than or equal to 1, return 1. Okay. If n greater than 1, so this is the done, return s of root n. So for this code we have to write the recurrence relation as t of n is equal to t of root n plus 1. T of root n plus 1. Okay, so here plus 1 is constant time for comparing and return value. Okay, now we are comparing our n value with this condition. If the condition is true, then we return the value 1. So for that purpose, we have to write it as 1. So if the condition is failed, so then go to the else part, return s of root n. So that if the condition is false, it returns s of root n. If the condition is true, it returns 1. So that we can write it as t of n is equal to t of root n plus 1. So plus 1 is the constant time required for comparing and return the value. Okay. So once we are writing the recurrence relation for that code, first we have to check this recurrence relation is in the standard form of master theorem. No, it is not there in the standard form. What is standard form? So standard form is, so t of n is equal to a into t of n by b plus, so theta of n power k log So this is the standard form. But so this recurrence relation is not there in the standard form. First, we have to convert this recurrence relation into in this form, in this standard form. So for that one, first let us take n is equal to 2 power m. So substitute in equation 1. So when n is equal to 2 power m, so this equation can be written as t of n is equal to 2 power m. 2 power m is substituted is equal to, so t of root n. So t of root n can be written as t of n power half. T of n power half can be written. So according to that, n is equal to 2 power m. So it can be written as t of 2 power m by 2. Okay. Plus 1. So n is equal to 2 power m is substituted in equation 1. So t of n is equal to 2 power m. So t of 2 power m is equal to, so t of root n can be written as n power half. Okay. So n is equal to 2 power m. So 2 power m whole power of. So it can be written as 2 power m by 2 plus 1. Now let us take t of 2 power m is can be written as s. So t of 2 power m can be taken as s of m. So t of 2 power m by 2 can be written as s of m by 2. Hence, the equation 1 can be written as s of m is equal to s of m by 2 plus 1. So this is equation 2. Okay. So this is s of m. So this is s of m by 2 plus 1. Okay. Now, so this is in the form of standard form. Now we have to apply the master theorem. Okay. So here this is the master theorem. So s of m is equal to a into s of m by b plus theta of m power k log power p into n. Now this recurrence relation is compared with standard form. So here a is equal to 1. So here there is no constant is there. So here a is compared with this one. So a is equal to 1. Here b is equal to 2. Okay. Plus theta of m power k log power p into n. Here m power k is not there, log power p n that is not there. So then k is equal to 0 and p is equal to 0. Once we have find out the a value, b value, k value and p value, now we have checked the condition a is equal to b power k, a greater than b power k, a less than b power k. Now a is equal to 1. So b power k is equal to, b value is 2, k value is 0, 2 power 0 is equal to 1. So clearly we can say that a is equal to b power k. A value is 1, b value is 2, k value is 0, 2 power 0. So 2 power 0 is 1, that is 1 is equal to 1. So by observing this condition, we can say that a is equal to b power k. Okay. So whenever a is equal to b power k, now we go for case 2. In case 2, so wow, there are three subcases are there. Which subcase is true? Here p is equal to 0. So then we go for third subcase. Okay. We go for third subcase because p is equal to 0, then 0 greater than minus 1. So s of m is equal to theta of m power log b power a into log power p plus 1 into m. Now substituting a and b values. Theta of m power log a value is 1, b value is 2, log power p value is 0, 0 plus 1, 1 into m. So theta of m power, here log 1 base 2. Log 1 base 2 value is 0. Log 1 value is 0. So m power 0 into log power 0 plus 1 is 1 into m. So m power 0 value is 1. So S of m is equal to theta of m power 0 is 1 log power 1 into m. So that is theta of log m. So this is equation 3. So now from equation 1, so n is equal to 2 power m. Apply log on both sides. So log n is equal to log 2 power m. So m into log 2 base 2. Log 2 base 2 value is 1. So that m into 1, that is equal to m. So finally we are getting m is equal to log n. So now m is equal to log n. Then this m value can be substituted in equation 3. Now we are getting s of m is equal to theta of log m value is log n. Log n. Okay. Here s of m can be written as t of 2 power m. S of m can be written as t of 2 power m. So s of m can be written as t of 2 power m is equal to theta of log n. Okay. Here n is equal to 2 power m. Then it can be written as n is equal to 2 power m. Then this equation can be written as t of n is equal to theta of log n. Theta of log n. Okay, so finally this is the time complexity of this recurrence relation. Okay, this recurrence relation can be obtained from this code. First of all, this recurrence relation is not in the standard form, so that we do not apply the master theorem. First, we have convert into standard recurrence relation. For that purpose, we have to take n is equal to 2 power m. So this equation can be written as t of 2 power m is equal to t of 2 power m by 2 plus 1. Now t of 2 power m can be written as s of m. Okay. So finally we are getting s of m is equal to s of m by 2 plus 1. So this is in the form of standard recurrence relation. Now this recurrence relation is compared with the standard recurrence relation. So then we are getting the values a is equal to 1, b is equal to 2, and k is equal to 0, and p is equal to 0, because this term is not there. Because of that reason, k is equal to 0, p is equal to 0. Now we have checked this condition. So a is equal to b power k. So here the condition is satisfied, a is equal to b power k. So once this condition is satisfied, so under the case 2, in case 2, which subcase we have to use? It is based on the p value. Here p value is 0. So then we go for case, in case 2, subcase 3. Okay. In the subcase 3, this is the time complexity. So t of n, we have to write s of n, because t of n can be written as s of m. S of m is equal to theta of n place, we have to use the variable m. M log m power log b power a into log power p plus 1 into m. A, b and p value is substituted. So then we are getting the s of m is equal to theta of log n. So now here n is equal to 2 power m. Apply log on both sides. Then we are getting log n is equal to log 2 power m. Here m into log 2 base 2 m into 1, that is equal to m. So this m value can be substituted in this equation. Then we are getting s of m is equal to theta of log. Here m place we are writing as m is equal to log n. So log n. So s of m can be written as t of 2 power m. T of 2 power m is equal to theta of log n. Here n is equal to 2 power m. So in this place we have to write t of n is equal to 2 power m. Because of that reason we have to write t of n is equal to theta of log n. Okay. So finally the time complexity of this code or this recurrence relation is theta of log n. Okay, so in this way, we have to solve the given recurrence relation whenever that the given recurrence relation is not in the standard form. So for that purpose, first we have convert into standard form. After that, we apply the master theorem. So in this way, we have to solve this type of problems. So thank you for watching this video. If you like this video, please subscribe my channel name. So D Srinivasa. So here D is nothing but DIVVELA.